Hi, my name is Talha Khan, and this is the Assessment 1 video demonstration. Begin with part A. I've just added comments to this section. I've not touched it. In fact, I start modeling from the constraint. And the first constraint I've put in is just to make sure that the pipe starts at the start location described in the or mentioned in the data files. The ending would then again be exactly where the ending is mentioned in the data files. Next constraint here, I've used the Manhattan distance, so right here, this formula, to check that the pipe is going orthogonally adjacent, so it's not going diagonal, nor is it skipping cells. The next constraint here I've used is to check on different steps on or iterative, but using the index rather, to check that the row and the column are not the same when compared throughout the pipe, uh, the path the pipe takes. I'm making sure that the pipe does not come back to a particular cell um, that it has, the path it has taken. Um, and then the next is just checking for the avoiding the negatives. So 0 and above. So we're checking the cost, and it has to be above 0. The next constraint here is just making sure that the total cost is either less than or equal to the budget that's mentioned in the data files. Then over here, I've introduced two new variables, Boolean type, right? It's is used and is adjacent, and I use them as such. So with this constraint here, I'm checking at a particular point if it exists in the pipe route, and if it exists, then is used as true for that particular point, RC. So that cell is true. And is adjacent would be, so I'm using the Manhattan distance again, just to calculate if any particular point is adjacent to the route of the pipe, right? So if it is adjacent to the pipe, then is adjacent becomes true for that particular point. And that really helps me to calculate the risk over here. But here, the total cost is as simple as just summing up the cost from the cost grid mentioned in the data files of a particular point. And then you have the total risk of any particular point is if it's true, if is true is true for that point, and then I'm going to use 2. If it is adjacent is true for that point, then I'm going to use 1. And if it's neither adjacent nor is it being used, then it's just 0, and we multiply it by the risk mentioned in the risk grid in the data file. So that'll give me the total risk. And the main goal is to minimize the total cost and the total risk. So I've mentioned that. And the output is right here. So if I was to run this, just clear the output. If I was to run this on, let's say, 2, piping route 2 data file. Yeah, and I'm using Chuffed solver as it gives me the fastest solution or process it fastest. I get that pipe has been the length is 1, 2, 3, 4, 5, 6, 7, 8. So it's gone through 8. And if I was to open the file, yep, the length here is 8, or it has to be 8. And then the total cost is 19, and the total risk is 32. Now, if I move on to the task B, or B1 rather, once again, everything is the same other than right here. I've introduced, so now we don't have a fixed length, it's variable, right? And as mentioned in the instructions, everything beyond can just be 0, 0, whatever is used. So I've introduced this used variable, and let the solver decide whatever is used. And beyond that, I've included 0 in the domain, just so we have the 0 index. And we could have 0, 0 coordinates beyond whatever is used. And everything else is the same. This is the same. And here right now, so whatever the solver decides, the end would be. So that's where we're ending it, right? I mean, although the end point is actually given, my bad. The solver, so we're just checking the used length, and we're not checking the entire set in the array. So we're not checking the entire array. Um, Same thing goes here. This is for row and column is not 0. So this is basically everything. So everything beyond whatever the used length is, we just assigning 0, 0 coordinates to them. Yeah. So used length and then +1, plus for 1 until the end of the length. So for example, we're using in data file 2 or piping route 2, we're using 8. And if the solver finds a solution, let's say 4 steps, then the other remaining 4 will just have 0, 0 coordinates. This is the same as before. We're using the Manhattan distance to check for orthogonal adjacents. And once again, we're not processing anything beyond the used length, right? So it's used length -1. Okay, next constraint we have is just checking for the loop. So it's just the same as before. Nothing was really changed other than I'm using used length instead of length, or len rather. And this one is just to avoid the negatives. So it's gonna be the cost. So it'll avoid all the negatives. So we're not going into any of the blocked ones as mentioned in the instructions. And this is just calculating the budget and making sure it's either less than or equal to the budget, the constraint. And same is is adjacent variables as before. This is doing the exact same function. And we're making sure that we check until use length, right? Because beyond that, you just have 0, 0 coordinates, right? And no, we don't want to have unnecessary calculations. And same with is adjacent. So we're just checking until the use length and nothing beyond that, because it'll just be 0, 0. Same formula as before. Yeah, same formula as before. This is, so once again, when adding up the cost, the total cost, I'm only checking until the used length part and not beyond that, because it'll essentially just be 0, 0. And although 0, 0 does not have a cost associated with it in the data files, in case it did, we don't want to have it accounted for here. And then we're just minimizing and then showing everything, also the used length. So if I was to run the same thing on the second data file, I would get, so we're using 6, 1, 2, 3, 4, 5, 6, and there's 0 zeros after. So 2 unused and 6 used. So the used length is 6. The total cost now is 12, so it's down from 19. It was 19, it's down to 12. And the total risk is 24, down from 32. So yeah, that was my video presentation. Thank you very much.